we implement a binary tree. A node of the binary tree occupies 3 memory cells. This is what we describe now. One has the type integer and it is called value, and we also have left and right branches. The predicate non-empty tree is a shorthand saying, at the moment, this is a binary tree node. It corresponds directly to how we define the data structure in Java. We also want to check that code that we usually write, such a constructor, corresponds to the specifications we write. In particular, the constructor has to allocate memory for a tree node. Now we want to be able to also talk about possibly empty trees. In general, a tree that is empty is represented by null, and a non-null reference must satisfy the predicate non-empty tree. That is, it must point to a piece of memory with 3 memory cells. Once we have this extra predicate, we can refer to it recursively, and so we make the predicate non-empty tree mean this is a non-empty tree instead of a tree node. Now, in order to be able to prove that the constructor is still correct, we must require that what we are being given as left and right are indeed trees. And as you see, we are forbidden to construct ducks, because the star in separation logic constrains possible aliasing. We can also attach abstract values to references. For example, we can attach a sum S to all the references that are trees. And we say that for empty trees, the sum is 0, and for non-empty trees, we delegate the computation of the sum to the predicate non-empty tree. The definition, of course, has to look at the sum of the left tree, the sum of the right tree, and add those up. Once we update the definition like this, we need to fix some of the existing specifications to say how the newly introduced abstract values are affected by the existing code. The modification here is rather trivial. The more interesting part is that we can refer to these abstract values to explain more functional properties. For example, we can specify a method that given a non-empty tree with some sum, returns that sum. A simple implementation is to simply add the value in the current node with the sums in the left and the right subtrees. jStar though tells us that there is a possible null dereference, so we'll have to rewrite the code in a way that makes it easy to check for null. Right now in an intermediate state, we see that the resulting value is incorrect. That is because we didn't add the left and the right subtrees. So in summary, we saw that jStar puts squiggly lines whenever we have errors that it can detect, and in this video in particular we saw possible null dereferences, violations of aliasing restrictions, and a little bit of arithmetic, which is done using an SMT prover.